Okay, maybe we can get started. So yeah, I'm proxying for Marlon to run the call, and as you can see from the introduction, Ravi and the team has presented this talk from the Face IT at the Gateway Computing Environments with the supercomputing late last year. So yeah, with that, I'll please welcome Ravi and the rest of the team, and then I'll let them introduce and get started. Ravi, please go on.
Yeah, thanks, Suresh. Hey, thank you all. I know a lot of you people, so yeah. So let me just sort of introduce myself. So my name is Ravi Maduri. I work at the University of Chicago and Argonne National Laboratory. I'm a fellow at CI and a product manager at Argonne. So this talk is about FACEIT, which is a science gateway that we've been running using Amazon resources for climate impact and crop modeling community. This is a joint work. As you can see on the title slide, we have quite a few people. It's a team effort kind of working on this. Raffaele and I started prototyping this capability a few years ago when Raffaele visited us from Italy. And then we started kind of collaborating with Joshua Elliott and Allison and Ian in trying to figure out if this could be applicable for the climate modeling, climate impact and crop modeling community. We wrote a smallish proposal to NSF and where we proposed that this would be a good idea, got funded, that got this effort started. I should also say that we also received a sort of a generous grant from Amazon Web Services, a research grant to stand this gateway up so that we could help the community. We could set up the gateway and get it going very quickly. So with that, let me just go through a few slides. I have some slides, and I'll try and show you a demo. And then maybe take some questions. So roughly the outline is, I kind of wanted to take a step back and describe the driving use case. There's sort of the vision that we've had at CI and at the Globus project, which is a science as a service vision, and kind of talk a little bit about the stack, the technology stack that we built to accomplish this vision, and describe what FACEIT is and why we kind of chose Galaxy to do this, and describe some of the customizations that we had to make Galaxy work for climate impact and crop modeling use cases, which involves adding a bunch of data types to Galaxy and adding a bunch of analytical routines to Galaxy, and how we went about building a community of researchers that leverage this capability. And so this is roughly the outline of my presentation. So as I said, our vision at the Globus project for the 21st century discovery infrastructure is that our goal is to provide more capability to lots of users, lots of researchers with low cost. And our goal is to provide these capabilities by providing scientific analysis or science as a service. So that's a driving force behind a lot of the gateway projects that we have going, is to make scientific analysis, data management, all of those capabilities available as a service, so that we can manage them, we can run them at a lower cost, and researchers can use them, and the overall sustainability goals of the projects are reached. So it's not a new idea. So we've been working on this idea for a while. In the 4 or 5 years ago, we used to call it service-oriented science, and this is a slide that Ian and I kind of worked on creating it. The goal, excuse me, at that time was that we would create tools that would help researchers create services, and these services could be discovered via a registry, and then you could compose them and publish the composition as a new service. So this is what we kind of postulated as a service-oriented science, and this is Ian published it in a Science magazine in 2005, and then we would outsource, or we would make use of infrastructure capabilities like TerraGrid to host these services. So as a researcher, I don't have to become expert in maintaining and operating these services and infrastructure. So this was the idea that got us started, and with the advent of cloud computing, and with the advent of some of the best practices that the industry has come up with to make services available to researchers at a production quality, we kind of leveraged some of those best practices in using cloud-based infrastructure to make capabilities available as a service, so that as a computational experts, we could focus on sort of the capabilities or things that we are really good at, which involves managing the service, running the service, and then we could sort of leverage some of the best practices in running infrastructure at scale from the cloud computing and other communities. So we applied these service-oriented science principles to the science as a service notion that we've been working on. So in the science gateways, we do have quite a few examples of successful examples of science as a service, science delivered as a service capability. So one of the capabilities that we made available as a service is called Globus Genomics. This provides next-gen sequencing analysis as a service. So it's been quite popular. We have a lot of users, researchers, labs, universities leveraging this capability at the production level and running and using it to analyze a lot of genome sequencing data. The next example is PDAX, which is the portal for data analysis service for cosmology simulations. This is a joint work that Saba presented this last week or a couple of weeks ago. Joint work with Salman Habib and Katrine Heitman, Tom Uram, Alex Rodriguez, and Berkeley Labs. So this is a sort of a service that we run at NERSC and at Argonne. At Argonne, it runs on the Argonne cloud called Magellan. The goal is to sort of, again, provide data and analysis for cosmologists across the world, so that they can reanalyze or analyze simulation data and do more science without having to themselves becoming computational experts in running these analysis. The third example is a cardiovascular research grid Galaxy, which is a science gateway that it runs on Amazon Web Services to do large-scale ECG data analysis. This is part of the NIH project for cardiovascular researchers. It's a service that we created that allows researchers who are doing who work in cardiovascular diseases to do large-scale analysis of time series data that ECG machines provide, and correlate those findings with the genotypic information, so that they can make discoveries that map the variations in electrocardiogram data, the variations, the heart palpitations to a particular genetic variant. It's a pretty interesting project, and we kind of run this service to do large-scale ECG data analysis. The fourth one is a traumatic brain injury. So in the same way we do. This is something that Kyle Chad and others have been working on to run image analysis, analysis workflows. Globus Proteomics is another science gateway, science as a service capability that we run that provides workflows and analytical capabilities for proteomics data. This is mass spec data that researchers get and then create these workflows to analyze this proteomics data. The next one is the eMatter, which is a material science data, which is sort of a science gateway for material science simulations. It's joint work with Dimitri Karpiv and others at Argonne. A bunch of material scientists and computational scientists kind of use this capability to run material simulations. And the last one is XSEDE, which is the topic of today's presentation. XSEDE is a framework that we built to advance climate and economic and impact and investigate the impact of climate change on crop outputs across various countries in the world, and assess the economic impact that the climate change will have on the output of food grains from these countries. Essentially, these are computational models where you would insert the projected output of crops across various countries and take into considerations the climate change or climate impacts on the outputs, and then present the sort of the economic impact studies using information technology. So let me just go a little bit into the high-level science stack that we have used to power these science gateways or science as a service. So we've used Galaxy as to interact as a portal, as a service, as a web front end that users who are not computationally sophisticated can use to assemble complex workflows. So we use it as a software as a service, so that users can assemble, can execute, can share, and discover workflows that others have created using a web browser. So to some extent, a lot of the users that we work with are very comfortable using a web browser because of all these new capabilities that we have going. And we build on top of, we use the Globus services as a platform as a service. We use Globus capabilities for data management, identity management, because, as you all probably know, our community has a lot of identities and have a bunch of credentials that they have to manage. So we leverage the capabilities that Globus provides in form of Nexus to manage those identities, and use Globus Transfer to enable rapid and reliable data movement into Galaxy. And we run all of these capabilities, the software as a service that we created on quite a few infrastructure. We use Amazon Web Services primarily for a lot of the gateways that I've shown you before. But we also use NERSC and Magellan as infrastructure providers. We do run PDAX and other capabilities on these infrastructures. And if you look a little bit into some of the tools and products that we use to make these services run, we use Condor, HT Condor for job execution. We use Chef, which is a configuration management tool to create recipes that we can reuse to launch infrastructures. We use Amazon. On Amazon, we use EC2, EBS, and S3, and simple notification services to keep this infrastructure going. On NERSC, we use a capability called Newt that Shreyas and others have really developed at NERSC to launch jobs and to manage the execution. The key capabilities on Amazon that we leverage is a spot market. We do leverage spot market that Amazon Web Services provides. Spot is unused capacity that Amazon Web Services provide to researchers or whoever at a very low cost. To sort of give you a sort of a rough idea of what the cost would look like, I could get a 32-core machine with 256 gig RAM for 25 cents an hour. Our sort of realization is that running things on cloud works really well when you have a data reduction problem. Say, for example, which genomics is. So if you have a lot of genomics raw data, you would run these analysis pipelines, and then you would get a so genomics, the input data sets are usually a few gigabytes or a few hundreds of gigabytes or terabytes, but the output data are a few megabytes. It works really well because then you don't have to pay for the outward network charges. We also use Route 53 to manage our domain name systems and our websites. And lastly, CloudFormation is what we use to sort of automatically scale up and scale down infrastructure and automate a lot of these capabilities. So the science stack that we have created is pretty agnostic, as you can see, to the scientific problem at hand. So what we do is we kind of have this stack that we customize for multiple domains or for the domain that we're working on. So all the gateways that I've shown you in the last slide leverage this science stack to set up the basic infrastructure that is required, and then customize these services with the various analysis tools and data types to make it very appealing to the end user. In this presentation, I'll talk about how we have customized our science stack for climate impact and crop modeling community. This is how we went about. So we call this science stack as Globus Galaxies, and we have sort of successfully adopted it to deliver these capabilities to the XSEDE community. So the sort of the lessons learned, or at least to some extent for us, the lessons learned were the combination of the factors. As you probably noticed on the beginning of the slide, we have quite a few collaborators that we are working with. There's a combination of this that resulted in a really great success for us. We have computational experts on team. This includes me, Ian, and others, David Kelly and others at the University of Chicago and CI. We have folks from agriculture and crop modeling community. This is Cheryl and her team from University of Florida from the agricultural science community. And we have Joshua and Allison, who are sort of these people who wear multiple hats. They're technology people, but they're also very much embedded into the community. So to some extent, we do have a pretty nice separation of concerns where folks who are on the computational side are really good at managing infrastructure, operating it, developing it, supporting it, and there are scientific community members, scientific team members who are really good at understanding the requirements that the scientists have in providing, in sort of shaping the service so that it is very much useful and applicable to the crop modeling and the climate impact community. So to some extent, if everybody does what they're good at, then the chances of us going far are pretty high. So that's what's really worked really well for us in the XSEDE project. Galaxy has been very useful for us because it's very flexible. We can extend it. We can add new capabilities to it. We don't have to. To some extent, the challenge is that we wanted the funding that we received from NSF was when we distributed it among ourselves, it was not a lot. As you all probably have very good experience, funding usually isn't really sufficient to sort of, so you kind of have to make the best of it in terms of, so the way we didn't want to develop a lot of new code, a lot of new capabilities that we have to support, because at the end of the day, it's really the support and that really it gets very expensive and kind of works against you in terms of long-term sustainability. So we leverage as much as possible what's available out there. So Galaxy has been very flexible in terms of us extending it. We added in Galaxy, we added a bunch of new data types that I'll talk a little bit about it, to customize it for the climate modeling and climate impact and crop modeling community. We added quite a few analytical tools, so that the community members, when they log in, they will clearly see the value they're getting from this gateway. We also added a bunch of new visualization capabilities, so that once researchers do the analysis, they can visualize the data. This is a lot of it is powered by D3.js, which is a JavaScript library for interactive graphs. And we also plugged in a bunch of community data providers into the platform. I'll talk a little bit about what this means. In the crop modeling community and in the climate impact community, there are a lot of open, publicly available databases that the users use to do comparative analysis. So we have created a nice and easy way to browse those data sets, data sources, and download those data sets and do interactive analysis. And then we built on top of some of the proven best practices in data management and execution management. This involves leveraging Globus services as much as we can, and use HD Condor and other capabilities that we know could scale really well. And finally, we had pretty, Cheryl and Joshua and Allison, our team members who are really plugged into the community, and go out and give workshops and demos. And we recently have done a workshop in Florida. We got like 100 people attend the workshop. We routinely do webinars and interactive tutorials, so researchers can get benefited from the gateway. So, I kind of talked about all of this already. So the participants, as you can see, are there's Raffaele from Italy, who's been really good at kind of converting, customizing Galaxy for climate data, which involves adding these data types and other capabilities. We have computational people from University of Chicago, Oregon, Florida, from the Agricultural Biological Engineering Department, Cheryl and her team, and Joshua Elliott and Allison from Department of Computer Science at University of Chicago. So teaching Galaxy to speak FACED. This involves, so as I said, the community, FACED community consists of crop modelers and climate impact study analysts. So what we've done is that we took, so as you probably know, Galaxy is meant for next-gen sequencing biological community. So we removed a lot of data types that are not applicable for this community, and we added a set of 20 new data types to customize Galaxy for the community that we are trying to adopt it to. This involves adding support for recognizing NetCDF files, which is a very popular data format in the community. ASEB, ACMO, PSIMS. These are all various data types. GeoJSON is an interesting. It's a data type that standardizes latitude and longitude and altitude and other types of spatial data. So we added all these data types to Galaxy. We added a set of interactive data exploration and data sources in addition to the Globus transfer tools. So within FACED, you can go transfer data from any Globus endpoint. In addition to that, we also added a bunch of custom interactive data exploration tools that I'll show you in a little while. This is for soil and climate data. PSIMS is a database that you could go ask for a latitude. You could give it a latitude and longitude, and it will give you the soil and climate data for that location. And the DAMIT data browser, which is hosted at Oak Ridge National Laboratory, we provided a custom interface so users can browse and get data from it. The AgMIC browser is something that the University of Florida team maintains, which provides agricultural data that is needed for researchers. We do have a growing number of analysis tools that we added that runs at scale on using AWS resources, and we are working on making it work on Open Science Grid and XSEDE resources also, using Swift and other capabilities. So as I said, some of the analysis tools that we have are AppSim, DSAT. These are all computational models that researchers use to do this analysis. And then a bunch of custom visualization tools which are map-based, so that once you do some analysis, you could populate a Google map or some plugin to see what you have done, what the analysis is telling you to visualize the results. We also have a bunch of charts, dynamic interactive graphs that researchers can plot and figure out what the analysis is telling them. One of the key things that we have enabled is some of the best practices pipelines for crop modeling. So researchers we work with are computationally very sophisticated, so we work with them to create best practices workflows. And once we publish them in Galaxy, others can recognize them or find them and reuse them. So in some sense, it's a lot of code reuse. There's a lot of you don't have to start from bottom. You can leverage somebody else's workflow to get to a point where the data is clean and you can do further downstream analysis. That is something that helps out the community as a whole in general. And then we run a lot of online tutorials. We do have a self-driven sort of tutorial that users can use to kind of learn how to interact with the FACET platform. So I took some screenshots of some of the tools that we have. The first picture on the left is all the data tools. These are browse and get data from various Globus endpoints, and the PSIMS interactive data sets for soil and climate, and the DAMIT browser, AgMIC browser. And on the middle screenshot is about various climate tools that we have, the computational models for analyzing crop model and climate data. And simulations for EasySim. This is something that was created at University of Chicago. Quad UI and plotting these various tools in custom D3 plots so that users can visualize it. So let me just quickly go through some screenshots. So this is the interactive data browser. This is very interesting. What it does is it goes to this crop database that Purdue and University of Florida work on maintain, and you can select interactively. You can select the location and the crop that you would want to get data and say download this data to Galaxy, and you can see on the right hand side the data gets downloaded using Globus transfers. So these are some of the best practices workflows that the community has created and published them, so users can go and reuse them and build on top of them. This is an example workflow that one of the researchers has created that uses PSIMS and soil and weather data and DSAT to sort of create run a computational model for a certain number of years as to what the impact of climate change has been on these crop models or crop outputs in various geographical locations. These are some of the custom visualizations. The sea surface temperature, you can see it on the left-hand side. It sort of provides a nice little visual interface to understand how these things have impacted various climate factors. More information, you could, we have a couple of sites. LearnFACET.org is where you could go and learn more about what FACET provides. And if you would want to use FACET, you could go to usefacet.org. and you can apply for membership, and you could do all the things that I've shown you. So as always, our work is sponsored by a lot of great people, good people, so that gave us funding to do this. And that's pretty much what I have. Thank you for your time, and I'll show you a demo or show you the site a little bit, and take some questions as I do that. Thank you.
Yeah, thanks very much, Ravi. I think very good overview of the gateway, and also some of lots of good background here. So yeah, so please jump in, everyone, with your questions. And I have few, Ravi, and I'll wait for the end.
Ooh, no questions. So I
all right. Hey, Ravi, this is Amit from XSEDE. Interesting work. You cover a lot of domains. I'm curious about the visualizations you showed. Are they being pushed through D3 or something else?
There's definitely we use D3 quite a bit, and Galaxy has a built-in. There's built-in charts that also use D3. There are some other visualizations that Raffaele developed. I don't know enough about what they do or what they use, and
So my question is kind of a little bit technical.
Mm-hmm.
I'm curious how the interactive visualization works when you are dealing with a lot of data. Let's say you have a ton of a .NET-CDF file and you create a map, right?
Sure.
How do you switch them, right? Because that imposes a lot of constraints on to fetch that file and generate that new map again. Let's say you have temporal data.
Yeah, let me try to see if I can show you how I can do that. There's actually some data sets here that you could visualize. I'm just trying to find if there's anything I can show you quickly. Yeah, let me.
The same thing with D3. I mean, D3 is nice, but as you know, if your data is more than a few megabytes, it gets hosed pretty quickly because the browser cannot process
you know
that.
what? The other thing we've done in the cosmology project, PDAX, is that we integrated with ParaView Web.
Oh, I see. Okay.
So that also is something that we want to sort of make it available for everybody. So ParaView Web, as you probably know, so we use it for cosmology, for visualizing cosmology data, and it's pretty nice actually. You could see, and it runs as a job on the NERSC nodes and shows interactive visualization. So for some lightweight or some graphing stuff, we could just use D3 to plot them. But for some serious visualization, we do have ParaView that we could use.
So is on the back end, is there some intelligence when how you decide what is going to be D3 versus ParaView Web?
So there's an icon here that shows visualization, and then in that icon, if I had some data that could be visualized, I could have shown you essentially it provides a sort of a choice of visualizations that you could use to run on this particular data type. So there is definitely intelligence that you can use to select which visualization.
Oh, I see. So you outsource that intelligence to the user to pick the tool, essentially, right?
Yeah, you can also, depending on the data type, you can also say, this data type cannot be visualized using graphs. You have to submit it to ParaView. So you can kind of do that decision for the user.
I see. Okay, cool. Thanks.
Hi, Ravi. This is Yan from NCSA. Excuse me. I have a question about your map-based visualization. For the data you displayed on map, did you need a mapping server on the back end to serve the map layers, or you just load them as a vector data directly from web server?
Right. So are you able to see my screen?
Yes.
So that's what I do to get the map data. So I think Raffaele knows a little bit more about this than I do. I don't. I know he has used Google Maps to get, but I think your question has much more detailed, much more detailed knowledge than I currently have. So if you send me offline, I'll get Raffaele to kind of respond to that.
Okay, so I ask this question because it is true that if the data size is large and if you want to load it on map, it might be very slow, and usually you need a mapping server on the behind to actually create the map as pixels, making things easier. But yeah, I'll talk to you offline.
Yeah, there's a WMS service that Raffaele said that he's using to do some of this mapping capabilities, but I don't know enough about it.
Okay, thank you.
So I just showed you the Daemit browser and how it's integrated. The Agmic browser is also pretty cool. So you could go and select some location and say I want to download data from. I probably have to select the crop. I don't know what grows where, but let me try. So you can select all the crops here, and you can say I want. And then you can, once you select the data, you can say I want to download this data into Galaxy. So this is something that you can interactively browse and get data for various crops across the world that are available in the database. And let me show you the Globus transfer stuff. So you can interactively select an endpoint where your data is, and then it will just give you a listing of the files. You can select one of the files here and then say execute. It submits a transfer, and then you get the data. And these are all the various analysis tools that we have that generates a plot. This is something. Let me see if I could just run this. And then there's a bunch of shared data, published histories that you could go take a look at. A researcher has recently done this, and you could go see what it does. And there are a bunch of errors there. You can go see what David has done. This is the PSIMS data and the soil JSON file. You can import this history, and once you import it, you can start using this history to do more visualization. Any other questions? Any other things that people want to see?
So, Ravi, this is Suresh. I'm curious on from the gateway standpoint, how is the community account-like model working here in the sense with Amazon EC2, and when you're supporting a community, so does the PI or someone provides an Amazon account and the community is free to use, or the community brings along their own? Right. Yeah.
So that's a very good question. So I'll talk a little bit about the economics of this. So we do have a research grant from Amazon for $20,000 per year to support this infrastructure. So since we use a lot of spot instances for analysis, and we only launch them when they're being used, the $20,000 goes a long way. So to some extent, the computational cost of this is, right now, it's not it's something we can do freely for the community, and once we do hit a sort of a threshold where the service has become really popular, and we're running or we're supporting hundreds and thousands of users every day, then that begs a question: if this is popular, then we can easily sort of create a sort of a spreadsheet that talks about what it takes to keep the computational to sort of what is the total cost of ownership of this service, and then that sort of gets us into investigating what would it take to sustain this. So right now we don't ask, users don't have to give any Amazon accounts or anything, but if a particular user is running millions of hours of CPU, then there's probably ways we could work with them to, if they're getting so much value from the service, we can figure out a way that we can launch this capability using their Amazon account, so that they can pay for, or they can be on the hook to pay for the capabilities that they use.
So is the Amazon grant renewable? So is that an annual thing you kind of renew?
Yeah, it is.
Okay. So on a technical side, so how do you manage these instances, because there's a cost, like when you start the instance and shut it down, right? If a user is trying to do a little job, I'm assuming you're not probably going and doing it somehow, bundling a bunch of jobs in one instance. How is that working?
So a lot of it is automatic, right? So we do, we have so the first thing is, we have this operational infrastructure that we use to monitor all these instances. So a lot of it's automated. So we use Chef to create them, to launch them. We use Nagios to monitor them. So if something goes down, we get an email and we get to see it. On the back end, we have a automatic provisioning framework that looks at a class ad for a particular application, does matchmaking, figures out what is the best spot instance that can run this analysis. It goes and gets that spot instance, spins it up, and makes it join the Condor pool, and then the job gets run. And we keep the instance available for an hour, because Amazon billing happens on an hourly basis. So if there are more jobs, the instance gets reused depending on how many. We can put as many jobs as possible on one spot instance and use it as much as we can, depending on the computational requirements of the tool that we're running. And if needed, we launch more spot instances. They get launched. And then once they're done, once they're idle for more than for an hour, they get released to the pool. So in that way, it's all sort of dynamic and automatic, and we only pay for what we use.
So how do you determine, how is this, if the spot instance is busy, means inside the instance, and if it's overloading, it's using too much CPU and things like that?
So a lot of this is so we profile these applications that we are making available from a computational perspective, and we have a pretty good idea of what is the kind of the CPU, memory, and I/O usage of these tools, and that determines the sort of the spot instance that gets launched. So if a node exceeds, or if an application exceeds a sort of certain parameters, that so essentially the application either exits, or the node to some extent it becomes really slow, and we do have monitoring capabilities that tell us if a job is taking longer than it needs to, and then we kind of look into it.
Okay, sounds good. A question from others?
I have a question. I wanted to ask about the Amazon grant that you received. So Amazon, wasn't aware of this, but Amazon has a program for.
Yeah, it does. Are you seeing my browser?
Yes, we can still see your sharing. Yeah.
I think it's Amazon. Let me just see if this works. I misspelled education. I probably need education. I think there's a website that you could go and apply for these grants.
That's excellent. And they give you cash, not just time? Is that?
Or
is it credit?
You're getting greedy here. No.
No. I just wanted to understand, because you said $20,000.
No. It's $20,000 worth of Amazon resources.
That's what I assumed, but when you said in a dollar amount, I thought, wow, that's.
Yeah, because that's how it's measured, right? That's the beauty of it, is that it's the computational resources have a dollar value associated with them.
And when you use it, it's like you're just using that as a compute engine that you're shipping the jobs out to, and you're not like doing like CloudMan. You don't have like your whole instance running on there as a virtual machine on there.
We actually do.
Okay.
Yeah, the head node or the node that's serving these pages, it's all hosted on AWS also.
Ah, very interesting. Okay. Very interesting. Thanks.
Mhm.
Yeah, just point to that. Like, and I think XSEDE has been also sending the dollar amount from like probably a few quarters, like on how much the allocation is costing. Or when the allocation is awarded, I think they mention the dollar amount.
I see.
So, Ravi, I had a question on the users, like, how you're using your Galaxy and then like the Globus Nexus combination. So you're bypassing the Globus user management and just plugged in the Nexus?
No. Actually, it uses the Globus. So I did log in as a Globus user, and then there's a group that controls the membership or access to this group. Let me just quickly show you what I mean.
Sorry, actually, I think they're confused. I mean Galaxy versus Globus. So there is a Galaxy user account here, like the Galaxy portal needs, and then the Globus or the Nexus one, right?
They are the same.
So so you plugged in the Globus user management to the Galaxies.
Yeah, that's correct. Yeah.
Okay.
Galaxy has a remote user concept that we use. So the user is set on the HTTP headers and gets passed on, and then we intercept it. We do token validation. We kind of make sure that this user is a Nexus user and is a member of a group. We have let me show you the groups that we created. There's a FACEIT group that decides decides access to this instance. So we have 72 people that use or members of this group. 68 active users. 4 are somebody just sent an email. Just approve it. Yeah, so it's pretty it's pretty good. I really like it.
So do you also need to make an entry in the Galaxy user table somehow, or?
No, it's all automatic.
Okay. No, I mean to say from the back end, like, does Galaxy, like, can Galaxy work with fully the Nexus, or does it also need to have some references in its Galaxy's own user tables?
We do it automatically.
So you do it, okay, as a programmer, okay. So
there's API for everything, so we just use that API.
So is this OAuth, all of this? OAuth?
Yeah.
Okay. Thank you.
I have one other question. The jobs that you all are running through this portal are like the ones we run in ours, our phylogenetic jobs. They can run maybe up to a week, maybe 2 weeks at a time. Are you running jobs of that magnitude, or are your jobs shorter or longer?
We run jobs that are a day or 2 days long, not a week, definitely yet. Actually, not in FACEIT, but in genomics, we have run. So let me just show you the genomics service also. So this is Suresh. This is what I meant. So when you get to an instance, it will ask you to authenticate using Globus, and it does the OAuth dance to use my Globus credentials to and does membership of the group to decide whether I could log into this instance or not. So what I meant, so we do have in genomics, we do run a few jobs that run for weeks. Sometimes they do run for a couple of weeks. Yeah.
Okay. Cool.
So how do you monitor all these jobs, Ravi? Like as a gateway administrator, you or someone else keeping a tab of like what's happening, if anything is failing, and so on.
We just if somebody screams loud, we will hear. I guess So we have Nagios. We have a lot of automated emails that get generated if something's or not. So we do monitor the infrastructure, and if that's so. For the jobs perspective, there's Galaxy provides a sort of an admin interface to monitor the jobs. So you can see if there are any active jobs. As an administrator, you can figure out what's going on. And sometimes I just log into the head node and do condor queue and figure out what's going on if something is if I see something is it's not going as planned.
Yeah, because seriously, I think I like Mark says when someone screams or someone reports that something is wrong, it's a gift. So when a user does that, so that way you'll know ahead. So it's more reactive or proactive? And I'm just curious on
a lot of monitoring stuff is very proactive, right? So if Condor is down, if a job is taking longer than it than the wall time says it does, and things like that, all of those are automatic Nagios alerts that get generated, and we get emails and pagers and things like that. So there's a lot of proactive monitoring. I mean, there's also a support email. So within Galaxy, if something is broken, let me show you what I mean. If a job fails, you can say, send this failure to the support at globus.org, which sends an email essentially to our Zendesk. So let me show you what I mean by that. So users can report these errors automatically and from within without actually moving away from the Galaxy interface. And then we track and we triage this, and then we assign it to people who are responsible for it. So anyway, so I was gonna find a ticket, but that's what we use.
Okay. Great. Any other questions? Sorry, I couldn't resist but ask Ravi. Do you guys like Zendesk or Jira or other things for the support systems?
Sorry?
What's your feedback on Zendesk as a user support system?
I mean, I don't have anything great. I mean, to some extent, I don't use it. I just triage it, and then for what I do, it works really well. I'll probably ask Gigi a little bit. Gigi does more work on it than I do, so I can ask her if you want.
Okay, that's fine. Just curious. Okay. Okay. Any other questions for Ravi?
All right, thanks a lot, guys.
Yeah, I'll take that a no, and thank you, Ravi, and thanks everyone. Have a good weekend. Ravi, I'll make this available to you and share you the link of this.
Okay. Thank you.
Yeah, please make sure you stop the presentation mode, stop sharing, and quit it so that it will be. Okay. Thank you.
Thanks very much.
Thank you. Bye-bye.